Biological aging is a mechanical process. Over time, the intricate physical structures of the human brain experience wear, and the raw speed at which neural networks process information begins to slip. This slowing of cognitive processing speed is a standard biological baseline, rather than a specific pathology. It is a mathematical certainty that every human brain eventually faces. Commercial brain training applications often ignore this clinical reality. These platforms routinely use aggressive marketing to promise age reversal, suggesting that digital puzzles can halt natural decline and sharpen the mind entirely. To strip away the commercial marketing and find the actual statistical facts, researchers rely on the ACTIVE trial. ACTIVE stands for Advanced Cognitive Training for Independent and Vital Elderly, and it serves as the definitive clinical lens for this field. This chart maps the unique scale of the trial. The x-axis represents patient age from 50 to 90, and the y-axis plots cognitive processing speed. You can see the natural biological decline on the downward curve, but the highlighted section shows where the ACTIVE trial tracked its subjects for over a decade, from 2002 to 2014. Tracking patients for 10 years is scientifically required because human cognition fluctuates. A patient might perform better on a test simply because they slept well the night before. To prove an intervention works, researchers need enough time to separate a true, sustained biological effect from the daily variance of statistical noise. The longitudinal data from ACTIVE proves that cognitive interventions do yield measurable results. However, those results come with strict, bounded limitations that redefine what we should actually expect from brain training. Knowing that the ACTIVE trial produced measurable results is only the first step. We need to quantify the exact mathematical impact these cognitive speed interventions generate. In clinical research, this impact is measured using Cohen's d. Cohen's d is a statistical metric that measures the standardized difference between two means, telling us exactly how large an effect is, regardless of the specific test administered. This diagram shows what the hard data actually looks like. The first curve represents the control group. The second curve represents the intervention group. Across longitudinal studies, cognitive training consistently yields a Cohen's d shift of between 0.2 and 0.5. For a patient, an effect size of 0.2 to 0.5 translates strictly to a small to medium clinical difference. It is a mathematically proven improvement, but it is a modest shift rather than a miraculous reversal of aging. What makes this data complex is exactly where that small to medium improvement occurs. The intuitive assumption is that speed training will universally improve a patient's raw processing speed. Looking at this bar chart mapping different cognitive domains, we see a paradox. The data often shows that the clinical improvements from speed training are actually more pronounced in adjacent cognitive areas, specifically in attention and memory, rather than in speed itself. The biological logic behind this transfer of benefit relies on system efficiency. Improving the brain's base processing speed acts as a neural catalyst. By processing information marginally faster, the brain clears cognitive bottlenecks, freeing up resources for attention and memory to function more effectively. This creates a trap for researchers. If a clinical study strictly measures processing speed, the data might falsely show that a highly successful protocol has failed, simply because the real benefit transferred into the patient's working memory instead. Firm conclusion. The data demonstrates that cognitive training does not universally upgrade the entire brain. It acts with modest force, selectively targeting specific cognitive pathways. Beyond the targeted cognitive domains, the data introduces another highly specific variable. The success of a protocol is entirely dictated by the subject's age. The demographic findings are clear. Cognitive interventions display their most pronounced, reliable efficacy when applied to patients in the 70 and older cohort. However, when researchers apply the exact same protocols to a younger, 50 to 60-year-old cohort, the measurable cognitive improvements are often statistically negligible. This directly presents a stark clinical tension. Why does a clinically validated protocol generate distinct improvements in an older population, but appear to fail entirely in a younger, healthier brain? Researchers define this phenomenon as the age baseline paradox. This graph on the left illustrates the mechanics of the 50 to 60-year-old cohort. At this age, a patient's natural cognitive speed is still operating near its biological peak. Because their baseline performance is already so high, the neural network has very little physical room left for improvement. When the baseline is naturally elevated, it mathematically obscures the small 0.2 to 0.5 delta generated by the intervention. The intervention is happening, but it is invisible against the patient's existing cognitive health. Now, looking at the right side of the screen, we see the mechanics of the 70-plus cohort. Years of natural age-related decline have significantly lowered their baseline performance curve. Because their cognitive speed has dropped from its biological peak, this lowered baseline provides the mathematical headroom necessary for the training effect to register. The 0.2 to 0.5 delta is now statistically visible and clinically relevant. Preventative cognitive speed training is not a universal shield against aging. Its measurable value is directly tied to the natural downward trajectory of the specific brain it is applied to. When we move from the tightly controlled mathematics of age cohorts into real-world application, we hit the problem of scientific reproducibility. A major point of friction in the literature is that identical cognitive training protocols deployed in different global studies often yield wildly divergent data. This happens because the human brain cannot be tested in a clinical vacuum. Every patient brings their entire external environment into the testing center. This network diagram illustrates the confounding matrix. This is the unavoidable web of external, uncontrolled variables that inject massive noise into longitudinal data. Seemingly minor variations in how a study is designed, or differences in the socioeconomic background of the participants recruited, cause the perceived efficacy of the protocol to fluctuate entirely. The matrix expands further when we account for profound lifestyle confounders like nutrition, physical activity, and social engagement. Daily nutrition directly dictates neuroplasticity, the brain's physical ability to rewire itself. Without the correct molecular building blocks, the brain simply cannot adapt to the stimuli provided by speed training. Baseline physical activity acts as a strict physiological prerequisite. Exercise increases the cerebral blood flow required to fuel the neural networks during the intense focus of cognitive gains. Finally, researchers track social engagement. Patients who maintain complex social interactions show a high correlation with sustained cognitive resilience over those who are isolated. It is clinically impossible to mathematically strip away these interconnected lifestyle factors to isolate the pure, uncontaminated effect size of the digital training itself. A patient's daily habits form the structural foundation of their cognitive health. This noise ultimately dictates whether speed training succeeds or fails. By analyzing the raw data of the ACTIVE trial and the limitations of the confounding matrix, we can synthesize a definitive, evidence-based clinical prescription. As a validated supplementary tool, cognitive speed training functions within narrow biological limits. It is a specific intervention rather than a comprehensive solution for aging. To achieve that 0.2 to 0.5 effect size, the data points to a specific clinical dosage: strict, focused practice for 15 to 30 minutes daily. Because longitudinal results take months or years to materialize, adherence is difficult. This is exactly why researchers utilize gamified application formats. The engaging interface is simply a delivery mechanism designed to keep patients returning to the protocol. Both practitioners and patients must abandon the outsized expectations set by commercial marketing. Success requires operating within this grounded clinical reality. This architectural model represents the final target state of all these interventions, the construction of a holistic cognitive reserve. Cognitive reserve is the brain's ability to improvise and find alternate ways of getting a job done, protecting against natural decline. To build this reserve, cognitive training cannot stand alone. It must be deployed synchronously. It acts as one pillar, holding up the structure alongside equal commitments to physical exercise, a nutrient-dense diet, and active social participation. Long-term defense against cognitive decline depends on the relentless multidisciplinary maintenance of the human machine. The evidence points toward a systemic approach, rather than a single digital solution.